Let's look at some optimization homework problems. Keep these things in mind as we are optimizing, find the optimal value. The idea is we first need to identify the equation that we're trying to optimize. So it could be product, it could be sum, it could be perimeter, it could be area. Whatever it is, we want to be able to read the problem and identify which equation are we trying to optimize. Once we find that equation, then we create, identify variables. Once we write that equation out, then it's a matter of trying to get that equation down to one variable. A lot of times there's enough information to help us make substitutions to get our equation that we're trying to optimize down to one variable. And once that happens, then it's just a matter of finding a way to find the derivative, set that derivative equal to 0, and solve for the variable. So for number 7 here, says the sum of the first number and twice the second number is 108, and the product is a maximum. So we're dealing with two numbers here, and we don't know what those two numbers are, but they may or may not be different. But we're just going to go ahead and identify those two variables for those two numbers. Let's let the first number be x and let the second number be y. Okay, we want the product is a maximum, so we know that we're looking to optimize the product. So if you see the word maximum or minimum, if those words are used to describe a specific value, then we know that that's kind of a clue as to help you decide which equation you're trying to optimize. So we're trying to optimize product, and product is simply multiplying those two values together. So the product of x and y would just be x times y. Okay, so we're trying to optimize our product equation. However, if you look at your product equation, we have too many variables, right? We're trying to get this down to one variable, and so that's where this second piece of information about the sum comes in handy. So we're told that the sum of the first number, we'll let that be x, and twice the second number, we'll let that be y. So the sum of the first number x plus twice, so 2 times the second number, is equal to 108. And we know the product is equal to x times y. So we have this equation available to us to help us get our product equation down to one variable. So if we know that x plus 2y is equal to 108, we can solve for, I'm going to go ahead and solve for x. It just seems like it's easier to solve for x. If I solve for x, x equals 108 minus 2y. If I make that substitution, I get p is equal to replace x with 108 minus 2y times y. So it doesn't matter if your product equation is in terms of x or y. We just want to get it down to one variable. Okay. So once it's down to one variable, if I expand this out, I get 108y minus 2y squared. So we found our equation. We've gotten that equation down to one variable, and now it's just a matter of finding the derivative, setting equal to 0, and solving for that variable. So p prime, okay, we're ready to find the derivative. We just go through power rule. 108y becomes 108. Negative 4y squared becomes negative 4y. Notice that we don't have to worry about d over dt or dy over dx. We don't have time being the independent variable, so there's no related rates going on here. We just find the derivative as we see it with respect to y. So p prime is equal to 108 minus 4y. We set that derivative equal to 0, and then we solve for y. When we solve for y, we get 4y equals 108. Y is 27. So when y is 27, we know that the p function is going to reach its optimal value. So optimal value is when the slope is 0. So it's either going to be a maximum or a minimum. In this case, it's going to be a maximum. So when y is 27, we're going to get to that optimal p value. And once we found that y value, we can plug into any of the original equations to help us solve for x. So I'm going to use this first equation here. We know that y is 27, so 2 times 27, subtract that over 108 minus 27 is 54. So y is 27, x is 54. So our product is at a maximum when x is 54 and y is 27. Okay, number 9. Find the length and width of a rectangle that has a given perimeter and the maximum area. So again, we look at context clues here to see that we're trying to optimize area. So once we determine that, then we want to create the equation. Let's go ahead and draw this rectangle here. I'm going to label the horizontal x, the vertical y. Area is just going to be length times width, so area is x times y. Okay. We're also told that the perimeter is 80 meters, so this equation is going to help us make substitutions, get it down to one variable. So perimeter is just adding up all the sides, so x plus y, so that's 2x plus 2y equals 80. I'm going to go ahead and solve for y, so 2y is equal to 80 minus 2x, y is 40 minus x. We can use this equation to help us narrow down our equation so we can actually find the derivative. So I'm going to replace y in terms of x, so y gets replaced with 40 minus x. If I distribute the x through, I get 40x minus x squared. That's our area equation. That's what we're trying to optimize. Let's go ahead and find the derivative. So a becomes a prime. 40x becomes 40, negative x squared becomes negative 2x. We set the derivative equal to 0. We solve for x. We get x equals 2x equals 40, so x equals 20. And then once we have the optimal x value, we can go ahead and find the other variable. So we can plug into the original equation. So 2 times 20, that's 40. 40 plus 2y equals 80. And then solve for y, we get 20. So area is at a maximum when x is 20 meters and when y is 20 meters. For 11, we're trying to optimize perimeter. It says find the width that will give the minimum perimeter. So we're trying to optimize perimeter. So in this case, we're trying to find out what will cause P to be at a minimum. So I put a star next to P since that's the equation we're trying to work with. So P is equal to 2x plus 2y. We know that the area is 32 square feet, so area is x times y, so xy equals 32. I'm going to go ahead and solve for y, just arbitrary here. So if I solve for y, y is 32 over x. I can use that information to replace y. So if I replace y in terms of x, then we have an equation that is down to one variable, and then we can get it ready to find the derivative. So I'm going to try and move this x up to the top. So I'll make this 2 times 32, 64 times x to the negative 1. And then we are ready to find the derivative. So p prime equals 2x becomes 2. 64x to the negative 1 becomes negative 64x to the negative 2. We set our derivative equal to 0. And when we do that, we just algebraically try to solve for x. So I'm going to move the 64 over x squared to the left side. Cross multiply. I get 2x squared equals 64. X squared equals 32. X equals plus or minus root 32, and I can simplify that to be 4 root 2. We're talking about width and length of a rectangle, so we know that we're only dealing with positive values. So 4 root 2 is our x value. If I solve for y, I can divide the 4 root 2 over, and y is 4 root 2, so perimeter is at a minimum when x and y are both equal to 4 root 2. Okay, for 18, a rectangular page is to contain 36 square inches of print. So I'll let the inside rectangle represent where the printed letters are. And then the margins are 1.5 inch on each side. So we know that the top has each of the borders are 1.5 inch from the border of the text. So I just went ahead and put 1.5 here to indicate that that's the length of all the borders. But if we think of it in terms of a rectangle, the full page is going to be x plus 1.5 plus 1.5. Right, so because there's a 1.5 border on each side, margin on each side, if I add the two margins together along with the x, that will give me the full length of my rectangular paper. So the horizontal length of this piece of paper is x plus 3, and then the text for vertically is y, and then the border is 1.5 and the other border is 1.5. So if I add the 1.5s together, I get 3. 3 plus y is y plus 3. So the area of this rectangular sheet of paper can be represented as x plus 3 times y plus 3. Okay. And we want to optimize the area, so we want to find the derivative, but before we do that, we have to find a way to get this down to one variable. So let's see what information we have. We know that we have 36 square inches of print, so we know that x times y is equal to 36, and that information is helpful because we can either solve for x and y, x or y, and once we solve for the variable, then we can plug in and we can simplify our equation down to one variable. So in this case, I decided to solve for y. Y is equal to 36 over x. I can make that substitution, replace y as 36 over x, and now I have everything in terms of x, and just a matter of trying to clean everything up before we find the derivative. So I'm going to expand by distributing the x through. So x times 36x plus x times 3, and then I'm going to distribute the second term. 36 times 36 over x becomes 108 over x. 3 times 3 is 9. So I've gotten rid of the parentheses for the most part. 36 cancel, the x's cancel out. So 36 plus 9 is 45. 45 plus 3x plus 108, x to the negative 1. If I bring that x up to the top, now notice that we are ready to go to find the derivative. Each term is nicely separated. There's no parentheses. All the variables are brought up to the top. We can just apply power rule for each of the terms. So to find a prime, we go through power rule with the first term, bring down the negative 1, subtract 1 from the exponent. 3x becomes 3, 45 goes to 0. We set our derivative equal to 0, and then we solve for x. So 3, bring the 3 over to left side, divide both sides by negative 1, cross multiply. We get x squared equals 108 over 3, which is 36. So x equals plus or minus 6. And but we're dealing with positive length, so x is equal to 6. So if x is 6, then we can use this equation to help us solve for y. So if x is 6, then 36 divided by 6 is equal to y. So y is also 6. We know x and y, they're both 6, but we're asking for the dimension of the piece of paper, not for the text. So the piece of paper is going to be 6 plus 3 horizontally and 6 plus 3 vertically. So the dimension of the piece of paper is going to be 9 by 9. 9 inches by 9 inches.